Our next speaker today is Marek Gluza, and Marek's going to talk about experimental observation of curved light cones in a quantum field simulator. Marek, floor is yours.
Hi, everybody. Good evening from Singapore. All right, so today I will be presenting on behalf of a larger collaboration and some results that we are working out in more details just recently. So I will first tell you a little bit about the system. The system has a very beautiful canonical physics, and then I will tell you about what it means that we are talking about a quantum field simulator. And finally, you will see the nice results obtained through the data taken by Amin Tajik. Here on the photo, he's the lead author of the publication that we are preparing. And I will be talking about curved light cones that we can directly observe in a one-dimensional gas of neutral atoms. So how does the system work? Well, if you take a gas of neutral atoms, you cool them down. If you zoom out a little bit, you will see this homogeneous fluid in some way. But deep inside, you have atoms fluctuating in and out. And the way to make sense of the system is not to get lost in the details of the individual atoms, but rather to think more hydrodynamically. We know that such systems are hosting waves. Those waves are basically acoustic waves, so phonons. And once you start thinking hydrodynamically, you need to be able to translate microscopical properties of those atoms into, for example, a density surplus that is traveling on top of the condensate. So such waves we describe as phonons, and there's a simple way of associating energy to phonons. So if the density dislocation is larger rather than small, then we will associate more energy to this wave packet rather than the energy associated with the small wave packet. And they also have velocities. I was showing this animation, and those waves are also fluctuating in and out, and they travel through the system. So now if we have a fast wave packet, which is quite big, it will have the largest energy, okay? And to make this more specific, there's a very clear formalism how to make sense of such a system through field theoretic modeling. It's called the Tomonaga-Lattinger liquid framework, where we look at the density deviation from the reference profile. So this is delta rho in my notation here. And the phase of the condensate is a little bit like the velocity. So if the gradient of the phase is larger at this position rather than for example, here, then we would say that there is some excitation of the fluid that is somehow faster on the right rather than on the left, signified by this arrow here. And if we think about those two observables, if we take the quadratic function, this is basically already here the Lattinger model. And what is important is here this reference profile, which you can often obtain as the ground state of the Gross-Pitayevsky equation. If that one depends on space, you are talking about actually a field theory where you are talking about a curved metric that you can use to set up, for example, the action functional for this model. So this is quite a simple model, but there's a lot of physics that you can do, and it can get also very complicated. So for example, you can think of building field machines, you can violate the Huygens-Fresnel principle. There's many things that you can discover in this model. So that's roughly the system. That was the physics of the system, basically phononic fluctuations. But the picture is actually bigger, because what Jörg's group is devising is actually quantum simulators, and there's a good reason to do that, because field theories are fundamental, universal, and effective. So if we would have systems which can simulate different field theories, we could answer really hard questions that we don't know how to do in theory very well. Here I'm only flashing out some references from the field. If you want to see different experimental developments recently, you can also scan the QR code or go to slides.com with my name. Those are clickable links, so I just flash it out here. The way you control the system is using the so-called atom chip. Basically, it's a structure with a highly conductive wire. Below that, you can constrain into one dimension the gas. And then additionally, there's this innovation of using a DMD where we can control the gas longitudinally. And that's what I will be showing to you today. So that's the experimental hardware that we use. Basically, the protocol will be taking a one-dimensional gas, splitting it, and then observing the non-equilibrium dynamics. And here we will see light cones from that quench. The way we measure the system is by performing interference. And that gives you the meaning of learning about the relative velocities in the system. So basically, if I will effectively see an interference profile which is flat here, it means that the velocities of the fluid fluctuations were aligned. And if it's jumping down, then it means that they were misaligned. Okay, so that's the interpretation of phase profiles. Those are the direct observables. And what we are doing in this project is based on a previous paper where Spiros, one of our collaborators there, pointed out that, okay, in field theory, the derivative of the phase is the velocity. Experimentally, let's look at finite differences. And that's what this project is about. And we are getting really nice results out of that. So what we will be looking at is basically finite differences of the phase, and they have the meanings of velocity. So it tells you that if the two-point function is positive, then the velocity fluctuations appear in sync. If they are, if the correlation function, the two-point function of those finite differences of the phase is negative, it means that they are shaking away from each other. So those will be two ways of looking at this. And then there's a simple way of understanding the pictures that I will be showing to you. There will be always a diagonal autocorrelation peak, and that one doesn't have so much information for us today. And then otherwise, if I see some correlation on the side, it means that there are two positions which don't have independent velocity fluctuations, and there's some coordination of what's going on in the fluid. If this will have a negative sign, then it means that there's an anti-correlation. Okay, so now I can show you the experimental results. So this is the protocol. We take two one-dimensional condensates, couple them strongly, then split and look at the dynamics. The observable is the interference. And if we look at differences of phase profiles at different positions, then we can extract those velocities and look at the estimator of the two-point functions. So those are the plots that I will show to you now. Okay, so what do we have? We have a gas which we can control to be homogeneous in the bulk, and then amine engineered hard walls here, which means that there will be a lot of reflections in the system. So initially, when he's cooling the system, you see this pattern here. Those are anti-correlations, which are everywhere throughout the system. Is a very clean signal. Then the quench happens, and what you will see is that basically here, this anti-correlation front starts propagating outwards. And what we get in the end is that the reflections from the boundary change the sign of the anti-correlation front. And I will tell you in a moment that this is actually the rainbow state that people also discussed previously in field theory. Now, the fun bit is that the system is so well developed that you can also engineer the profile to have, again, hard walls, but be curved. And when it's curved during the quench, you actually develop a little bit of a curvature in the front here. And basically similar dynamics with the reflection happens. Another thing that Amin constructed is what happens if you don't have a sharp edge and it's decaying smoothly. And what happens is that actually there's no reflections, and basically we lose the signal. So it's a little bit like the entire fluctuation gets absorbed into the edge. And that also has some meaning in curved spacetime field theory that I actually don't have time to talk about today, but you can discuss with me. I'm happy to discuss with you about the interpretation of what it means that we actually don't see those reflections anymore. Let me show you the reflections again. So now it's the first scan in the flat box, where this is here kind of flat up to my drawing. And then you will see that you develop a front that is moving here outwards. So this is going further, further, further. And as it's going further, we have this reflection here on the side. And now this reflection is actually propagating inwards, while the anticorrelation is going outwards. We can actually explain why the sign shifts from blue to red, because it's a reflection of the velocity from the edge. Almost there. And now I want to show you what happens when this anticorrelation, when this antidiagonal front comes here. So the interpretation would be that with those dots, we had this shoelace anticorrelation pattern. So initially the thermal state was kind of like intertwined in this way, but through those reflections, we get a nice rainbow state. Because if you think of those patterns, what happens here is that this antidiagonal front basically means that I have a rainbow state. So basically, I have a huge amount of correlations between left and right parts of the system. That's a really beautiful result that we get from this new idea of looking at those velocity estimators. Other stuff that Amin was able to extract is when we have a smooth edge, basically we start losing the front completely. There's no recurrence. If we have a hard edge, we know that we have a recurrence. So this is what you see on the right when we have the recurrence, and here we are losing the recurrence, which is constructed by the experimentalists. You can program this in using the DMP. And finally, the statistically significant results that we are getting is we can really extract that the velocity depends on the geometry of the density of the gas, which means we achieve first steps for really controllably quantum simulating field theory in a curved metric background. So this is the meaning of those statistically significant plots, where the curvature of the density is really controlling what the velocity is doing, which means we get those curved light cones that we can see in the system. So that's the quick talk for today. And I invite you really to contact me and have a more deeper chat with me. Thank you.
All right, thank you very much, Marek. We have time for one question. Okay, I see Masahiro. You have a question?
Hi. Thank you very much for a nice talk. Your experiment is very amazing, I think. And I'd like to ask you about the regime of your experiment. So I'm wondering, your experiment is still in a classical regime or quantum regime? So can you observe the quantum fluctuation around some configuration?
Yeah, so the experiment is you take a three-dimensional Bose-Einstein condensate, squeeze it, and you cool still in the trap. And basically the extracted temperatures are around 50 nanokelvin. At those temperatures, the thermal state doesn't really have many quantum correlations in it. And it's quite consistent with a classical field approximation. So there's one paper about mechanisms of gaussification that I mentioned in the middle of the talk. We discuss it much more in detail there, that is consistent with classical field approximation. So the thermal state preparation doesn't have visible quantum correlations as far as we know. But once you have this rainbow state, so I was showing you a commutative observable at a fixed time when you have the rainbow state. So for sure, the statement is that you have extensive classical correlations because that's what you extract. In my PhD, I developed tomography for those phonons, but it's much more difficult to extract entanglement, and I cannot make any positive statements about quantum correlations in the system. It's much more difficult to. It's a little bit like asking of taking a classical light bulb and shining it through a waveguide. A classical thermal light will not give you much entanglement, and those phonons are quite close to being classically thermal. It's quite close to Boltzmann distribution. Yeah.
Thank you very much. Very clear. Thank you.